All right. Now, this is one approach to thinking about the consumer's problem, and it's probably the most natural approach because it seems to fit with the way we look at the world, right? That is, I got a budget, I go out in the marketplace, I got a bunch of goods I can buy, and so this maximization problem kind of looks directly at what I as a consumer might think about the problem I face. Turns out there's another way to look at this that's very helpful and actually has a lot of its own empirical applications, and that is to turn the problem around and consider what we would call the cost minimization problem. So the cost minimization problem is, in mathematics, would be the dual of the problem we just talked about, would be, let's find a bundle to minimize the sum of the xi pi subject to u of x1 up to xn equals some specific utility level u bar. All right? So we've tried to turn the problem around. Instead of saying, what's the maximum utility I can get for a given income, I've turned it around and say, how much income do I need to achieve a given level of utility? Now, people understand why those are dual problems? People understand why those solutions are going to be related? Right? It's x1. Think of the two good case, x1, x2. I got this solution. This is u of x1, x2 equals u bar. This is some m over px, p1, m over p2. And you might ask, is this guy maximizing utility subject to that budget constraint? Or is he finding the least budget he needs to get to that level of utility? And the answer is, I don't know. Looking at the picture, I can't tell you which one he started with. But that same point is going to characterize both of those, right? That is, this is just going to be a dual way, reverse way in some sense of looking at the same problem, right? You could say, I wanted to get to this indifference curve and I kept switching my budget in until I got to the minimum budget that would allow me to get to that curve. Or I started with this budget and said, what's the highest curve I can get on? Those two things are going to end me at the same point. Right? People see why those two problems are so closely related. All right. So how are we going to solve this problem? Well, we can look at the Lagrangian for this problem. L is the sum of the xi pi plus I'll call a different multiplier mu, u bar minus u of x1 up to xn. Okay, so that's my dual formulation of the problem. I'm now going to minimize cost subject to a utility constraint, reaching that level of utility. Now, there are real-world problems for which this might show up. You might say, look, I'm trying to get an employee to move to someplace else from where he lives now, and he has a certain salary and level of utility where he is. In order to make him at least as well off in the new place, and they have different prices, I'm going to have to give them a different level of income. I mean, how much income do I need to give him to allow him to be as well off living in New York as he would have been living in Chicago? That would be the kind of question. How much of a bump or decrease in income can I get away with sending him to New York instead of living in Chicago? All right. Any questions that people have? All right. Now, what are the first order conditions? Well, we take the derivative with respect to each of the x's, and those derivatives are going to be pi minus mu partial u, p1 minus mu partial u partial x1 down to p1 or pn minus mu partial u partial xn. These all got to be 0. And u of x1 up to xn, of course, has to be equal to u bar. Okay. Those are my corresponding conditions than what I had before. Now, I can rearrange these to be P1 equals mu partial u partial x1 down to Pn equals mu partial u partial xn, and of course just that same constraint, u of x1 up to xn equals u bar. Now, the thing to recognize is that these n equations are exactly the same ones I had before. It's just got mu in place of 1 over lambda, right? Mu is just the same as 1 over lambda. And therefore, that same interpretation that margin utilities have to be proportional to price has to hold for the cost minimization problem, just like it did for the utility maximization problem. For the same reason, right? If I got more utility per dollar on one good than another, then I should shift my dollars to the one that gives me more utility per dollar. I mean, it's the same question. It's not even a different question. And that's why both of them are characterized by this tangency, where there's the same slope between the budget line and the indifference curve. Everybody understands that, right? It's the same equations. Same equations. Now, the only difference is I'm finding a solution of, so the way I think about it is there's a whole bunch of these solutions that look like that, right? Take the two good case. I got that solution, I got that solution, I got that solution, I got that solution, I got this one over here, right? I got a whole bunch of these solutions. There are all these tangency conditions that are representing for some value of mu that satisfies this equation, right? Those are all those solutions, are all these ones, which are the same set of solutions I got here. And then what I'm doing differently is just how I'm labeling those equilibrium points. In the one case, I'm labeling by the utility level you're on, and in the other one, I'm labeling by the budget line you're on. People get the idea? It's the same set of points, it's just one case it's indexed by the utility level, and the other case it's indexed by the budget level.